This is EE3450 Lab 9 UART communication with host PC. We start by initializing our UART. For experiment 1, the baud rate was 115,200 with an 8-bit no parity check 1 stop bit. Exercises 1 and 2, the baud rate was 57,600 and similarly 8-bit no parity check 1 stop bit. BRDI, which is the baud rate divisor integer, and BRDF is for fractional, were found to be 52 and 5 for experiment 1. These values will be shown later on how they were found. And we come down here for number 1. For number 1, we're going to be enabling the clock to UART module. Our module is 0. Step 2, we disable UART enable pin. We temporarily disable the UART baud rate generator. That is right here. Step 3, we write our IBRD and FBRD, which is the baud rate divisor integer and fractional. Step 4, we configure settings for the UART frame. We have 8-bit no parity check 1 stop bit FIFO enabled. Step 5, we configure the UART clock source.
Hey, there he is.
And step 6, we re-enable anything we need for the UART. Our transmitter, receiver, UART enabled again, and the system clock divisor. This is the setup GPIO for Lab 9. Couple things were needed. Port A for the UART communication. This was found from the data sheet, which will be shown later on. Port K was used for PWM, and port M was used to control the separate LEDs. We had to initialize those clocks. For port A and K, we had to set the control register values 0x01 and 0x06, which were also found in the data sheet. We had to set the alternate function select bits for A and K. The DRR, the direction of pins for M, pin 1 and 0, port M. And we had to indigenously label all those ports and pins.
What? No.
This is the initialization for the PWM used to control the motor. For Lab 9, we'll be using module 0, PWM 6, generator A. Our system clock is 48 megahertz. The divisor using is 4 with our PWM frequency at 600 hertz. The load value was found to be 20,000, which is loaded down here. We had to initialize our module 0 for the PWM. We're enable the clock divider and choose our PWM divisor. Disable the PWM blocks and timer setup counting mode. Once again, load or input our load and our CMP value. We set it as a left align PWM. We enable the PWM box and the countdown mode, and we enable the PWM output. This is experiment 1 for Lab 9. The main part of the code, we simply define a couple character variables. We set up our UART initialization and GPIO initialization. We change our system clock to 48 megahertz. And in the while function, we're just going to continuously be printing out hello, my name is Raul Zapata in our termite command window, and always calling our print screen function with the 500 millisecond delay. Come down here for print screen function. It's just simply calling our char, which is a pointer. We're going to check if it's the null character. If it's not, then we continue. This while is just a small buffer to check if our FIFO is full. And then we just keep on outputting each character of our print screen, and constantly adding 1 to S. This is for the Lab 9 exercises 1 and 2. First, we start by defining our start and stop character and our structure here, which is our state machine. We define our CMD size, which is to be 20. And in the main part of our function, what this function is going to be doing, it's going to be changing from state to state, right? Idle, record data, or execute. And simply just based on the commands, either LED on, off, motor on, off, while motor to the duty cycle on, off, it would do that through UART communication, serial communication. And depending on what state it's on, it's going to do whatever the state wants. We start by enabling a couple of character variables: ch no line, ch return, and ch integer I. This is from Lab 1. Our state machine and our data length to be 0. We set up our system clock to be 48 megahertz. Set up our UART, GPIO, and PWM initializations. And our while loop, we're going to come. And first thing we're going to be doing is actually going to be checking if our FIFO receive flag is empty. And then we're going to come to our cases here, which is our state machine. We have idle, which when is ch equals the start character, it's going to set our data length to 0 and take our state to record data. In record data, it's a little bit more complicated. We have many if statements. We start off to check to see if our data length is bigger than our CMD size, which is 20. If it is, it goes back to idle. If our ch is our start character, our data length is set to 0. If it's a stop character, we do the command of the data length set to 0, and we switch to the state exe, execute. If we have the return character, do this and we add 1 to data length. If our ch does not equal 0, then we print out whatever ch is and we add 1 to the data length. For execute, we just do our function execution, and then we do go back to the idle state and we wait 10 milliseconds. So let's go to our executable function, which is down here. Okay, so here we define our two variables, our duty and our PCH, and we're going to be using strcmp, which is just string compare. It's going to be comparing the command that was given to the state LED1 on. If it is exactly the same, then the output will be 0. And when that happens, we're going to be turning on our GPIOM bit 1. We're going to set it to a 1, which will turn on the LED. And this command is going to follow all the way through. This very same logic. We're going to be comparing the strings, and if it equals the same, the output would be 0, and we would do that command. So here is turning on LED1. If the command and LED1 are the same, then we turn off LED1. It should be 1. If we put the command as LED2 on, then we will turn on LED2, and similarly when we say LED2 off, we will turn off LED2. Here, down here, we're going to be doing our motor control. We're going to set PCH equal to strtok command and delimiter. If it doesn't equal the null PCH, then we string compare our PCH to their fan, whatever we're going to be inputting in the termite window. And see down here, we're going to get our duty by setting A to I of PCH. Where if our duty is equal to 0, then that would be our CMP that would stop the motor or the fan, and we will print out the fan is off. Otherwise, we would change our CMP to this value from our given duty, and it would set our CMP to whatever duty cycle we want. So if it's 50, it will convert it to 50% CMP duty cycle and turn on the fan. This is the calculations for lab 9. Here we're going to be calculating different BRD int and fractions for experiment 1 and then also for exercise 1 and 2. For experiment 1, the system clock frequency was 48 megahertz with a UART divisor of 8. So the frequency of the UART clock is just the frequency of the system clock divided by the UART divisor. 48 divided by 8 is 6, so we get 6 megahertz. And with our chosen baud rate of 115,200, we get our BRD to be FUR clock divided by the baud rate, 6 megahertz divided by 115,200. This gave us 52.083, and we split up this BRD to BRD int and fraction. Our int is just the whole number, 52, and our fraction is just the fractional part, or the remaining part of our BRD, which is 0.83. And then we use, we define our UART IBRD for our main code to be BRD int 52. And the UART FBRD is just an integer of the BRD fraction times 64 plus 0.5. So the integer, or 0.3 times 64 plus 0.5 is 5.812. The integer of that is just 5. That's how we got 52 and 5 for our UART IBRD and UART FBRD for experiment 1. For exercise 1 and 2, the LED and motor control, it's similar stuff. The frequency of the system clock stays as 48 megahertz. The divisor kept it as 8. That's a high speed one. So our UART clock is the same as 6 megahertz, but our baud rate was now 57,600. So our BRD became 104.16, where BRD in is 104, and then the fraction is 0.167. I plug it into the formula, and I get UART BRD to be 104 and UART FBRD to be 11. Next is going to be for the PWM initialization. We have the system clock as 48 megahertz, or the frequency for the PWM we're going to be using is 600 hertz. The PWM divisor is 4, so we find our frequency for the PWM clock to be 12 megahertz, which is 48 over 4. The frequency of the system clock divided by the PWM divisor. We find our load value by taking our frequency of the PWM clock and dividing it by the frequency of the PWM. So 12 megahertz divided by 600 is 2000. And then our CMP value at 0 is first, we need to calculate this one because that's going to be our initial value. So it's 20,000, but we subtract 1 because we don't want it exactly at 20,000. This is using termite for experiment 1. As you can see, the baud rate was set to 115,200. Communication port 3. That's the only one I have that is connected to our TIVA board. Write 8 data bits. Stop bit is 1. No parity check. We have the pen CRN11. Cool. So for experiment 1, when I reset my board, the string "Hello, my name is" Raul Zapata will be printing out continuously from my computer. So, as you can see, it is printing it out at a 500 millisecond delay. Let's clear it so I can redo it. Still printing out. This is for experiments 1 and 2 for lab 9. Turning the LED on and off. We have 2 separate LEDs. They're going to be turned on and off with our commands. And then we have our fan right here. It's going to be commanded to be at 50%, 100%, and 0% duty cycle. Our connections to our chip, the motor chip, to our TIVA board. It's going to be TM0 on the purple far left, TM1, TM0. The blue is PK4, and it's grounded, right? And then it's connected to all that to our power supply. We're going to be inputting commands on the termite window. This right here, you can see the baud rate is now 57,600. As mentioned in my code before, the baud rate is different for experiment 1 and exercise 1 and 2. So we have a different BRDI and BRDF. Same thing though, still 8 bits, 1 stop bit, no parity check. And let's start. Let me load the code. Okay. So it's gonna be LED on, LED 1 on. Let me check actually. LED 1 on, LED 2 on, fan at 50, LED 2 off, fan at 100, LED 1 off, and then fan at 0. Right, so those are the commands, and that's what's going to be doing with these components. So let's do LED 1 on, enter. LED 1 is now on, and as you can see, LED 1 is now on. Let's input LED 2 on, LED 2 on, so you can see when I hit enter, LED 2 will turn on, and it says LED 2 is on. Perfect. Now we have to have the fan at 50, so this fan right here is going to turn on 50. Fan at 50. Okay, then we turn off LED 2. LED 2 off. LED 2 is now off, and it is, the blue is off. Then we're gonna go to the fan at 100. So the fan speed is gonna pick up. There we go, it's at 100. You clearly see it rotating a lot faster. And then turn off LED 1. As soon as I hit enter, LED 1 is going to turn off. Perfect. LED 1 is off. Right, these are the sequences. And then the last is turn off the fan. Fan duty cycle 0. When I click enter, the fan will stop spinning. There we go. And as you can see, the fan has stopped completely.